Hello, and welcome to the eTech podcast with me, your host, Ryan Maughan. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. For today's episode, we're joined by Dan Murphy, who's a technical marketing manager from ST Microelectronics. Dan is based in the UK, but he supports the team in Germany. Welcome to the show, Dan.
Hi, Ryan.
So could we just start off by finding out a little bit more about you, Dan, and your personal background?
Yeah, sure. So my background with regards to electronics goes all the way back to Bromley College. So I started out life doing a BTEC in electrical engineering.
Right.
And then from there, I went on to university in Sheffield to study electronics. And then in my final year at Sheffield, I specialized in solid state electronics. So this is getting into the detail about how electronic circuits are formed on silicon. And I also specialized in power as well, part of my final year.
Okay. So don't take this the wrong way, but back then,
yeah.
What was the kind of inspiration? What attracted you to solid state electronics as a thing at the time?
Well, I think I was just interested in how the silicon all goes together and the processes and that type of thing. And then in the lab work, I was quite interested in the power products. So, I mean, this is going back a while. So transistors were rated in ohms rather than milliohms back then.
Yeah.
So that was my main focus at university. And for my final year project, I actually did a study on the degradation of ohmic contacts at high temperature. So the university were able to find quite a good project for me to work on. So that was very interesting as well.
Oh, fantastic! And then when you graduated from Sheffield, where did life take you after that?
Well, so like a lot of people in their 20s when they finish university, so I had a couple of jobs in quite quick succession. So I started at a distributor in Surrey, a specialist distributor for passive components, and then I moved very quickly on to what was Siemens passive components back then, which is obviously FCOS now.
Right.
I was there for a few years, and then after that I joined ST. So I've been in ST for 20 years now. So.
Wow.
It's quite a while, yeah.
Yeah, you must have seen an awful lot of developments and changes over that time.
Yeah, a huge amount of change, just in the products that the company is producing. And if you look at where ST is today and where it was back then, I mean, we have huge business on product areas now that didn't even exist when I joined the company, which is interesting. So obviously silicon carbide is one of those, but another one is MEMS. I remember MEMS really starting to begin in production in sort of 2005, 2006.
Right.
And yeah, it's very interesting. And this was obviously the Nintendo Wii came out.
Right.
I don't know if you remember this console and this handset you waggle about.
Yeah.
So, this was one of the...
For the benefit of the listeners, what is MEMS?
So MEMS is... It's essentially an electromechanical device. So you have a metal structure, and it's basically measuring movement. So a 3-axis MEMS sensor is measuring X, Y, and Z axis, and then an accelerometer is measuring height G. You can have sensors that measure yaw and tilt, and pitch as well. So what makes this up is essentially a mechanical element, and then inside the sensor, you also have a digital portion, which is converting the movement into a digital output.
So these are like little teeny weeny, tiny microscale, not quite moving parts, so sort of almost moving parts, but not quite inside a microchip, basically. Which are now, I mean, it's amazing now, the products that have MEMS sensors in it, they are everywhere, absolutely everywhere. From you might even find one in a fridge door. Certainly mobile phones have got these things in.
Yes, and it really evolved. It started with just measuring 3-axis, and now you measure temperature, pressure, and the accuracy is quite incredible. In smartphones, they measure the difference between what floor you're on in a shopping mall or something like this.
Quite extraordinary. And it's kind of interesting technology in terms of how they manufacture those sorts of devices. The same with when you started out. Did you foresee that electronics now is sort of everywhere, and particularly sort of power type devices are everywhere? We've gone from like the humble light bulb being a incandescent filament to then fluorescence with sort of some electronics around it to now LEDs, where it's sort of power electronics and drivers and embedded software, or even in a light bulb, through to practically everything that we touch and is around us is absolutely stuffed full of electronics. Is that something that you kind of could you see that coming, or has it just kind of crept up on you?
To an extent, but what I didn't see coming is just to the extent it could proliferate into literally everything in daily life. I mean, like you say, it's in door handles. They've literally put electronics everywhere. And what I certainly didn't anticipate was how the birth of the smartphone and apps that go on smartphones would accelerate this process. So I think the technology we have today, so the use of apps, and people have really grasped how electronics can go hand in hand with that. Certainly the last 10 years have been quite mind-blowing.
So just for people who might not know, I'll put some links in the show notes to your profile and also to ST. But could you just give us a quick sort of top line of ST and who you guys are?
Yeah, sure. ST is a broadline semiconductor manufacturer. So it's a French-Italian company. So back in the early 90s, SGS Semiconductors, as it was back then, merged with Thomson Semiconductors to form ST Microelectronics that we have today. As I mentioned, it's very broad line. So the main markets we serve are automotive, industrial, consumer, and also infrastructure markets. And the devices, the product areas we play in are very broad. So we have everything from 32-bit microcontrollers to power transistors, discrete products, MEMS products. It's quite incredible. And the evolution of the company is very interesting for me as well. I mean, if you look at how ST is viewed by the broader markets, if you go back 20 years, broadline semiconductor companies were viewed as, high growth, leading edge, et cetera, and because of the proliferation of silicon into literally everything today, it's almost now viewed as a defensive stock. So people who work in hedge funds, that type of thing, it's amazing how it's transitioned from this sort of up and down type marketplace to a defensive one, because whatever's going on in the world, the products are always needed.
Yeah.
They're in everything.
Yeah, definitely. And ST is pretty big, isn't it now?
Yes. So the turnover last year was just under $10 billion. So very big company. We have 46,000 employees worldwide. And what's interesting is approximately 20% of those employees are working in research and development. So we have a huge number of people working on new products, new ideas. And then that's reflected in the number of patents. So the ST has over 18,000 patents.
18,000 patents?
Yes.
Blimey.
And yes, that are used in products that, are serving over 100,000 customers worldwide.
Wow. And it is, because in the semiconductor world, in the silicon world, you've got sort of companies that do research and development and kind of subcontract out the manufacturing, and you've got companies who supply, do the manufacturing as well. Where does ST sit on that? Are you a full service company, or do you outsource manufacturing, or do you have your own in-house?
No. One of ST's strengths is very much that we have all our own processes. So for sure, we do outsource some of our manufacture, some of our front-end manufacture to big foundries, but generally we're known for having our technology in-house. So we up to 28 nanometer in digital, it's all in-house in ST. And then all the power technologies are in-house, all the BCD technologies and the silicon carbide. So it's a very good mix. So we're not at the mercy of third parties necessarily.
Right. Okay. And before we kind of get into the main topic that we'd agreed to talk about, which is silicon carbide, when can you just sort of touch on, when you say broad line, what kind of what are the sort of key products? If you like top 5 things that ST sell, where are we likely to find them?
So first of all, your smartphone, you'll find ST inside. So that's obviously a very well-known product. I mean, we all have one pretty much.
Yeah.
And then also in your car. So pretty much whatever car you drive, ST will be in your car somewhere. So
right.
I mean, a high-end car can have up to $1,500 of silicon inside it now.
Wow. And that will be power switching devices, micro...
Yes, everywhere. So in your entertainment system, so in your stereo, in your satellite navigation, so the obvious areas people would think of, but also in the door of your car, there's drivers to lift the motor up, to lift the window up and down, to demist the mirrors. The possibilities are really endless. But for automotive, the big mega trends for ST are obviously autonomous driving and the electrification of cars, because both of these areas require a huge amount of silicon content. So this presents a huge opportunity for us. Yeah,
clearly. And that, so then just to segue that then into silicon carbide. So this is, something that we're starting to see come into the market more and more. Some pretty major vehicle manufacturers using silicon carbide switching devices. Could you tell us more about what ST is doing in that field? And you very kindly offered to kind of do a bit of a run through of what we mean when we're talking about silicon carbide as well. So
okay. Yeah, sure. So silicon carbide, just to explain what it is a little bit and why it brings so many benefits, it's a wide bandgap material. It's relatively new. And there are some physical properties with silicon carbide that don't exist in silicon, that bring huge benefits. So there are many of these, but I'll just talk about one or two to keep it simple. So the first difference is the electric field strength. So this is the ability of the device to address a certain voltage. So silicon carbide can address much higher voltages. So, for example, if you consider, just for argument's sake, you have a transistor that is 650 volts breakdown. As a silicon carbide transistor will be able to address this with a much smaller area.
Right.
So just physically a much smaller piece of silicon carbide than you would need if it was silicon. So that's one of the first key points. Another key attribute is the electron mobility or electron velocity of silicon carbide material is much quicker than silicon. So the benefit this translates into is we can run at much higher switching frequencies.
Right.
So when we're working in the space of power conversion, this translates into much lower losses, because as well as having this ability to switch much faster, the switching is much cleaner as well. So the wave shapes are a lot cleaner, and they're less lossy than traditional silicon technology.
Right, and it really is the sort of what we're talking about is a conventional transistor is made using silicon, and that's fabricated to create the transistor. And with silicon carbide, it's literally we're replacing that basic silicon with the silicon carbide instead. And we're fabricating a transistor out of that improved material.
Yes, yeah, it's a completely different material to work with. So, for example, if you draw some comparisons in production, a silicon wafer is annealed at 800 degrees. Silicon carbide, it's 1700 degrees. So the processes are at much higher temperatures. So if you run ion implantation, this is done at a much higher temperature for silicon carbide. It's 500 degrees C compared to 25 degrees for silicon.
Yeah.
And then also you need more accurate photolithography processes to define the structures on silicon carbide.
Yeah.
And then when you're trying to produce the structures, it's more difficult because you're working with a harder material. So it's a more complex and difficult device to produce.
Yeah, because the other application where silicon carbide is used quite a lot is things like hard coatings on cutting tools and drill bits and things like that.
Yes. Yeah.
So by nature of the fact that it's being used as a cutting tool, it's not the easiest of things to work. And
no. So they yeah, and this is where a lot of the investment is going in now, is into the manufacturing of this material. So the benefits are clear. The market is clear for us. We see really huge growth potential. So there's a lot of effort and development going into improving the yield and really reducing the cost of producing the components.
Right.
And then that in itself means that it will proliferate and bring a lot of business for ST. So. Right.
Yeah, because that is one of the... So if we look at applications where we might use silicon carbide devices, so obviously like replacing conventional transistors with silicon carbide transistors is one of those. And your explanation there was excellent. I didn't realize that at all, actually, in terms of the driving thing being the electron velocity. But you've got a better switching device, basically. So we've got a more efficient, faster switching device that we can also operate at higher temperatures than a conventional silicon device. So that's pretty useful in applications like traction inverters and power conversion devices, so chargers and DC-DC converters, where we want to switch the electrical power either to spin a motor or to put it through a transformer to convert voltage from one level to another, etc. So pretty useful devices, but the kind of big thing with silicon carbide at present is it's quite a big cost penalty to a conventional device.
Yeah.
So you've got to kind of know, especially in automotive, where cost is one of the really important factors, and particularly electromobility, the sort of constraints to that really taking off. It's all about getting that cost performance trade-off right. So yeah, interesting to know what you think is going to happen with the cost of silicon carbide devices over the next few years.
Yeah, okay, that's fine. We can chat about that a bit. So already over the past few years, I'd say the price evolution has been quite mind-blowing with silicon carbide,
right?
In terms of just how quickly it has already come down. But as you correctly state, it is still more expensive than silicon. But what we need to be doing is looking at the entire system cost. So you mentioned a traction inverter in an electric vehicle. This is really a very good example to use. So if we consider an electric vehicle that's running on a 400 volt bus, for example, if we use silicon carbide instead of traditional silicon technologies, we can expect an improvement in efficiency of maybe 4 to 6%, something like this. So on the face of it, that doesn't sound like a huge amount. But if you then extrapolate that and you start looking at the cost of the battery, so let's say the battery is costing you $150 per kilowatt hour.
Yep.
And you have a 60 or 70 kilowatt hour battery. So if you take 6% of that, you very quickly cover the cost of implementing silicon carbide. You start saving $200 on the cost of the battery. This covers the additional cost of wide bandgap components. So this is the view we have in ST, and this view is reinforced by car manufacturers now. So we see a very strong move to silicon carbide coming from car manufacturers from sort of 2024 timeframe.
Okay.
Yeah, so it's clearly heading in this direction.
And is that in all devices? Because I know with some OEMs, there's often a bit of a debate about, well, we might use silicon carbide in the DC-DC converter because we can really maximize the benefits, but they're not in the traction inverter. But are you seeing people go across the board with silicon carbide?
We're seeing it across the board. Right. So particularly where you're dealing with higher levels of power. So if someone's developing a 3.6 kilowatt OBC or something like this, maybe superjunction silicon FETs are the way forwards. Maybe if you really get into the detail of the design, it can still be done at a lower cost with this approach. But if you start looking at what major car makers are doing now, which is to integrate the auxiliary converter into the onboard charger, and if you look at that then being integrated somehow into the battery system, we're seeing the use of silicon carbide extensively now. So where you have an OBC plus DC to DC converter, and it's running at a relatively high power. To do this just with silicon switches is actually a challenge now. This is what I see with one or two of my customers, and if you then also factor in the reduction in cost of silicon carbide over the past 3 years, it's really becoming an attractive proposition now. So.
Okay, so you see it as it's sort of technology that's facilitating further improvements. So because that's just sort of mentioning it in passing there, but that's quite a huge topology development that's starting to come through. That the move from just a separate charger DC-DC to a more integrated device where you've basically got one item that's doing both tasks. That's a pretty new concept.
Yeah, so it depends on the vehicle manufacturer. So European car makers tend to work with a kind of platform approach. So having one box that fits all is advantageous for them. So we've got one or two RFQs running where they're doing precisely that. And then also with the traction inverter, what we're seeing is people having different ideas around you maybe fit an inverter onto the rear axle, and then that would go in every single car. Mm-hmm. And then for bigger vehicles, you have a second inverter on the front axle. So car makers are really trying to plan ahead a little bit more in this way. Whereas I think a few years ago, it was more about this looks interesting. We'd better get an EV out into the market because everyone else is. And I don't know that they were thinking of it as strategically back then. They certainly are now. And I had a call with a car maker a week ago, and the guy said to me, the plan is by 2027 to cease production of combustion engines. And I,
wow,
my chin hit the floor a little bit. Because you can, I guess you can see it coming, but when a customer tells you that, it really hits home.
Yeah, no, we've certainly had similar kind of conversations, and it is. I think people don't see that in terms of the development cycle is quite long. In automotive for vehicles, they're big, complex things with a lot of engineering. So you're looking, 3 to 5 years to get a product from concept onto the roads. So people are working on, and I'm sure you are working now on vehicles that aren't destined to be on the roads until the mid 2020s. As are we. So it's a very long kind of lead time into things being in the market and tested and proven and all the sort of reliability work done, and it's not an easy job as people are finding out. It's an interesting comment in terms of people in the last few years maybe rushing to get products out and not thinking all that strategically about how they can best implement an electrified powertrain. That's What do you think? Why do you think? What do you think's driven that? They didn't take it seriously before, or
I think what we've seen over recent years is new car makers appearing. So if you look at Tesla, for example, they made over 300,000 cars last year. And I think 10 years ago, if someone had said to you, a car company you've never heard of is going to produce 300,000 electric cars, we'd all be raising our eyebrows a little bit. But here we are today, and they're doing this. And if we look particularly at China, there are other vehicle companies popping up. For example, NIO produced over 10,000 electric cars last quarter. So they're running at 40 to 50,000 vehicles a year.
Yeah.
And the advantage that these companies have is they don't have the legacy that traditional car makers have. So if you're producing millions of vehicles in a certain way with a combustion engine, and you're completely geared up for this, and then all of a sudden you're faced with managing this kind of transition, it's a really a huge challenge. And it's obviously much easier for the new entrants because you're starting essentially from a blank piece of paper. And it's really shaken up the automotive space.
I always say I think there's a different design approach for an electric vehicle. There's with a combustion engine product, it's difficult. The design challenges are different. But there's almost like a different approach. You can afford to be a little bit less, a bit more siloed. I think that's probably the better way of putting it. You've got the powertrain guys over there and the sort of chassis guys over there, and they kind of don't often have to talk to each other.
Yeah, it's completely different. It's and for some companies, it's presented a huge opportunity. So if you're a big company producing transmissions for traditional cars, you're looking at the EV space and thinking, well, hang on, we can attach the motor to this and develop an inverter, and perhaps as well we make steering and we produce braking systems as well, so we can ship an entire axle to someone with everything on it.
And that's interesting. And what do you think in the industry the mood is towards, whether OEMs will bring it in-house, or whether they'll continue to work with the big tier ones? Do we see a future where, because you mentioned you were on a call with an OEM, so are OEMs going to start to take responsibility for designing their power electronics and making them and motors and integrated axles and things, much like how they make engines now? Or do you think they'll allow the sort of transmission companies or the other tier ones to who owns that space? It's a bit of a land grab at the minute, isn't it?
It's exactly that. The OEM I spoke to last week, they're actually bringing this in-house. So the inverter they will develop in-house.
Right.
They will use a tier one for the transmission, but then it's very unclear, really. It's still quite fragmented. But I imagine, like always, at some point there will be some kind of consolidation, and there will be a pattern to how this unfolds, and it will almost certainly be driven by cost, as it always is. So
who can get the economies of scale where? And that's an interesting one with what ST makes. So something as fundamental as a switching device. Would you ever see the potential for OEMs to start making their own switching devices? I know some, like Toyota, are quite heavily involved in switching devices now. None of the other OEMs, to my knowledge, really have gone down that path. But is that something that might?
It's not something I necessarily see a car maker doing, because this isn't really where their added value is. But there is a possibility, and we do see what we refer to in the business as tier ones. So these are people that make the equipment that go into the cars. We see them investigating or making switches and modules and these types of products. Because as the cost is quite high, it can be an interesting business.
And that could be whether ST will move up the value chain in the future and start to supply more kind of complete module units?
Yes, well, we are doing that. So we're developing modules to address traction inverter application. So this has already been being done in ST. Also, lower power modules to address markets such as OBC and DC to DC power converters. Because this is another thing. Customers have different ideas about the best way to produce these products. So, for example, for an onboard charger, customer A will be very much along the line of just using discrete components. You'll have another customer that will use modules. So they will literally screw modules onto the board, and then it's treated kind of as building blocks.
Yeah, it's more of a mechanical assembly task.
Yeah, correct.
Yeah, which is fine if the module does what you want it to do. That's the often challenge is that I guess the modules will tend to be designed with one high volume OEM in mind that sort of pulls the product through, and then if you can adapt that to do what you want in your application, it's can bring some good advantages. But if it doesn't quite do what you need, then you either have to put extra hardware around it to adapt it, or to use discrete parts instead.
Yes.
We started talking about silicon carbide and how you would use it, and I think I distracted you massively, and we went off down some really interesting areas there. But so we're talking about silicon carbide for a traction inverter. So what we're establishing is, what ST sees as the trend is that silicon carbide will be widespread as a switching device in high power and lower power devices, so traction inverters, DC-DCs, and onboard chargers. Where would you start, in terms of like a good design for a silicon carbide device, and what are the major differences when you're approaching a power design with silicon carbide instead of a conventional device?
Which sort of application area do you mean? Do you mean for traction or for,
let's concentrate on traction
charging?
Inverters.
So I mean, obviously the starting point is the power rating of the inverter. So what we need to do is run some calculation based on the top level of power, or peak power as it's called. So which will be typically maybe twice the average power. And then what you're trying to do is break that down into phase current. And then basically you go through the various levels, and then you arrive at a point where you're determining how many switches will be needed. So essentially in an inverter there are 6 switches. So you're then into trying to calculate how many die or pieces of silicon carbide would be needed per switch. And then this then drives you in a direction of working out which approach you want to adopt. So some customers go for a big module, which has many die inside it that are sintered down onto a copper substrate, and then you have mechatronic welds on the top for the source. This is a relatively easy solution to implement, because you obviously have everything inside the module, and then you basically overlay the gate board on top of that module, and you build up vertically, and then you have a traction inverter. Or another approach is to use discretes. So we have a very high performance package that we've developed, which is essentially a mini module. So it's two die inside, and it's a very high performance discrete switch. And then you're beginning to work out how many of those you obviously need. So what also comes into play here, and is a very important consideration, is the stray inductance inside what we call the commutation cell. So this is the full loop.
Right.
So although the switch is very powerful, and you might decide, okay, 2 of those in parallel would be okay, the reality is you'll end up using 3 maybe, because by using 3 you reduce the headline figure for inductance.
Right.
So inductance is a very key consideration.
And just why is that? What does that drive?
If you think of stray inductance, is if you're driving along in your car and someone starts pulling the handbrake up.
Right.
This is how I like to think of stray inductance. It's stopping the current moving around in an efficient way, and it's generating heat.
Right.
So you need this parameter to be as small as possible.
Okay.
So if we work very closely with third-party module manufacturers, and they have, some of them have very innovative ways of keeping this figure down. It's quite impressive. And this is one of the key considerations in inverter design.
Managing that stray inductance. Keep the handbrake off.
Yes.
And so it's interesting that even at that fundamental level there, you've got two clear approaches, one using a module and another using discrete components. I often hear people talk about, there's then a kind of trade-off in terms of some people like to load share across devices, and other people get a bit worried about that. So they try and use the biggest switch possible to carry the current, to reduce the number of devices and reduce the load sharing. Whereas actually, I have seen people kind of use it as a kind of inbuilt thing where they're trying to load share across lots of smaller devices, and they'll go for a smaller device for each switch, and an array of them, rather than a single big device, or maybe two big devices to make that switch.
So with high power applications, there's essentially no choice. So if you're developing a 150 kilowatt inverter, there isn't one piece of silicon in the world that can handle that amount of power or current. But of course, when you parallel the switches, it's a bit self-regulating, the load sharing, because obviously as the switch gets hotter, the resistance of the switch increases. So the current in that part of the circuit will find its way through a switch that is a bit cooler.
Yeah.
And then that switch will heat up, and so it self-regulates to a certain extent.
And because silicon carbide is a bit more thermally stable than conventional, I would imagine that is somewhat easier with a silicon carbide device. Yes, yeah,
it can cope with higher temperatures and a lot more stress than a regular switch. So
yeah, and in we've got these sort of quite different characteristics with silicon carbide, faster switching, higher electron velocity, all that good stuff. Does that drive a different approach to the other elements of the inverter? So do you need to sort of handle the gate drive differently, or is there more chance for, do you need to do different stuff with a DC link, for example?
There's one or two considerations that need to be considered. One of the key things, obviously in a traction inverter, is you need to develop this with an element of what we call short circuit withstand time. So in a short circuit event, you obviously need to switch it off. So if you're using silicon devices, so IGBTs, the period of time you have to make this transition is a lot longer than you have if you are using silicon carbide.
Right.
So although the silicon carbide essentially is easier to drive, dealing with the short circuit withstand time is a bit more challenging, because you will be trying to do this in 1 or 2 microseconds in a very short space of time.
Okay. And why is that?
It's just because of the different properties between IGBTs and silicon carbide. Okay. So IGBTs are very robust in that sense, and that's one of the qualities they have. But then the huge downside is, if you want to work at much higher voltages, it's very difficult with IGBTs, and obviously you can't switch at the same sort of frequencies. Like people are running inverters at 8 or 10 kilohertz with IGBT technology, and you can run at more than double this with silicon carbide.
Right.
So then the knock-on effect there is, you can use smaller DC link capacitors.
Yeah.
There are huge savings to be made. I mean, if you're using silicon carbide in an inverter, you can realistically expect to house it in a space that's half the size or something like this.
Wow.
So the reduction in form factor,
and that's
significant.
Not just, you mentioned that the silicon carbide devices themselves are physically smaller, but most of that size reduction will be driven by the other parts in the circuit, right?
Yeah. So if you just focus on the chip size, so by using silicon carbide, the silicon area that's needed to produce the inverter will be maybe 1/5 of the size.
Oh wow!
Yes.
Yeah. Okay.
And as you rightly say, this then knocks on further down the chain of the design to other areas, the cooling that's needed, and the cooling system, and the other elements that make up the whole product. And then you end up with this much smaller, neater brick, if you like, producing the power.
Yeah. And when you're switching a silicon carbide device, does it you've got this advantage is this fast transition from being on to off, but does that kind of make a harsher transition? So you need to sort of absorb that elsewhere in the system, or kind of soften that out to is it hard switching basically, or can you still kind of create nice waveforms?
No, you can create sort of nice clean waveforms. So generally with wide bandgap technology, this is one of the advantages. Going a little bit off piste here, but if you consider something like a gallium nitride switch, I've seen a demonstrator where I think it was a 1 kilowatt PFC, and what the company had done, they had literally removed the silicon switch from the PFC, and in a really crude and dirty way put a gallium nitride switch in. So they didn't augment any of the gate drive or the housing or implementation. They literally just did a like-for-like swap.
Yeah.
And then this produced a significant improvement in the efficiency. So they didn't increase the switching frequency. They just replaced the switch. And because the switching is so much cleaner,
right,
there's less bounce, and you already see this improvement. So there's all these conversations about switching up at 2 megahertz and this type of thing, and to realize the benefits of these technologies, you don't necessarily need to do that. Just the cleaner switching waveform already brings a benefit.
Okay, and interesting. And so from a design angle there, sort of covered. So there are some things to take into consideration, but actually, in a lot of ways, it should be almost an easier task to design with silicon carbide compared to a conventional transistor.
Yes, in general, yes, it should be.
Okay, so you and I are both up for getting beaten up by the world's electronics engineers for that. You hear that, guys? Silicon carbide's easier to design with than IGBT. I'll put my helmet on next time.
I know where you're going a little bit. There's considerations around the gate driving. You've obviously got to generate this higher voltage. You need some sort of flyback, but again, the technology is evolving, and the threshold for driving is reducing a little bit, and it's becoming more and more in line with silicon technologies, I think, as time goes by. So.
On the sorry, I meant to ask at the time, and we started talking about something else. So when we're talking about the short circuit properties, and you need to basically detect that, is that all about essentially monitoring the current flow in the system and like fast detection of a short circuit?
It is. It's exactly that. So you're monitoring the current flow across the switch, and then in the short circuit event, you're needing to very quickly turn the switch off. So this you need to consider with the gate driver design. You need to be looking at all the propagation delays and these elements. But from what we see from our customers, they're able to do this, and there are very good gate drivers becoming available on the market for silicon carbide. So there are drivers becoming available with things like the flyback controller integrated into them, and all sorts of features in the hardware of the gate driver to assist with developing your system, if you like.
Go on.
No, I was just going to sort of finish that remark with saying, and also particularly for chargers and DC to DC converters, these products aren't expensive, in my opinion. The cost is quite low. So more and more, I think the whole idea of using silicon carbide is just becoming more and more attractive, as everyone gets on the bandwagon, if you like.
And that drives one of the other challenges that exists at the moment, which is availability. So like one of the things that we see is very, very long lead times and sort of constrained availability of devices, as the sort of big OEMs are obviously pulling millions and millions and millions of devices onto their schedules. What's ST doing about that to keep open?
So yes, we can talk about this. That's a very good point. So I'd open the discussion by saying what ST is doing is investing very heavily. So the increase in capacity that we're anticipating isn't, relatively large percentages. It's 5, 6, 7-fold increases in capacity.
Wow.
So there's various ways of doing this. So at the moment, we're producing on 6-inch, and like others, we will progress to 8-inch wafer technology.
Yeah.
But also just putting in additional capacity as well.
Right.
One thing that ST's has done, which was in the news last year, is we acquired a share in a company in Sweden that produced silicon carbide wafers. So we're actually moving through the vertical, if you like. So we're
right.
investing in the production of the substrates as well as the device development and fabrication. So the investment isn't just in producing capacity of normalized products; it's in the whole supply chain.
Okay.
So, and I noticed on LinkedIn this morning as well, there was a nice picture of one of our largest competitors building a huge fab somewhere.
Yeah.
For silicon carbide. So I appreciate it's a concern some people may have, but I from what I see, people are making the investments. ST for sure, and also our competitors are as well.
Interesting that you mentioned about going up a wafer size. One of the challenges that we did a podcast a while back, actually with a competitor to ST, and I remember one of the comments that they'd made was that so the issue with power devices is that with a microcontroller you're constantly getting volume improvements through the product development. So as the processor gets smaller and smaller and smaller, you can make more and more and more of them on a wafer. But with power switching devices, that doesn't follow through. It's you need a certain surface area for a certain amount of power, and that's it. There's not much you can do about that. Is that a kind of? Do you agree with that? And that basically the answer is just literally more manufacturing capacity, or do you see ways of squeezing more out of less?
No, you're absolutely correct. So in the digital space, if you like, very small piece of silicon can do a huge amount. But in the analog space, to move amps around requires die. It requires physical area. So, but having said that, you can get some improvement. So you obviously, when we go through different iterations of the silicon, so we're currently beginning to roll out Gen 3, which is our third generation of silicon carbide. There is a improvement in the figure of merit. So the RDS on per area improves, and the capacitance and ratios improve. So that translates into more devices per wafer.
Okay.
But your observation is, in general, completely accurate.
Right.
The only way you can move hundreds of amps around is with lots of silicon. So that's why we're investing heavily in increasing capacity.
Okay. Really interesting. Fantastic. So just to bring things to a close now. So what does the future look like? What does the product roadmap look like? What's kind of new and exciting that's coming? And what are you most excited about in the next year or so?
So to talk about the products, how they're looking. So we're continuing to innovate the silicon. So to striving for improvements in the figure of merit of the actual die. And what's exciting for me is some of the ideas we have inside the company around the packaging, how to enable the silicon, if you like. So there's topics such as dual side cooling, and we're looking at ways to make modules fit the applications better. I can't go into too much detail, but we have a project running with one or two customers that's very, very innovative in terms of how you extract the heat from the switches and reduce the costs. So it's really moving very quickly. And for me personally, what's interesting is the strategic programs that I'm working on with the bigger customers, and really getting these into production in 2 or 3 years' time. It's very technically challenging. We've talked quite a lot about the inverter application, and having spent 2 decades working in electrical engineering, I now find myself almost having to transition into mechanical engineering somehow. And you're looking at cooling plates and how things go together, and that's an interesting challenge for me, and something very new. So
oh, fantastic. Well, that's been really fascinating. We've covered like so much ground there, and I've learned a huge amount, so thank you very much for agreeing to take the time out today to talk to me, Dan. That's been great. Thank you.
No problem. Thank you very much for the invite. Thank you.
Great. So that's all we've got time for today. That's been absolutely fascinating talking to Dan, learning more about what he does, about ST, talking about silicon carbide and how that's going to be used and the sort of roadmap that's coming. So the basic summary from that is, if you're not working on silicon carbide now for your power devices, you should be. Keep a look for some really interesting products coming from ST, particularly on the module side, with some of the companies they're working with on repackaging. That's really interesting stuff coming through there. So, like as always, please leave us a rating, hit like, comment. We really appreciate it. It helps to get the podcast seen by more people and keeps us up there in the rankings. If you've got a question or a subject that you'd like us to cover, do feel free to get in touch. We've had some fantastic reach outs over the last month. We've got some really exciting, interesting podcasts coming on some topics where people have got in touch with us. So feel free to get in touch. And that's all. So that's all we've got time for today. I really look forward to speaking to you again soon.